All right, welcome back, everyone, to the deep dive. You know, we love to get our hands dirty here, metaphorically, of course, and really dig into the fascinating processes going on in the biotech world, and today is no exception.
Yeah, we're really going cellular level today.
Exactly. So, you sent over some really interesting material about this technique called high-pressure homogenization.
Ah, no.
And, before we really get into it, I think it's important to lay out kind of the mission for today's deep dive. We really want to understand how this technique lets us get at the good stuff, all those valuable materials that are trapped inside cells.
Mhm.
But we want to do it in a way that, doesn't get too bogged down in the super technical details.
Right. We want to keep it,
Yeah.
high level so we're not getting lost in the weeds, but still getting a good understanding of what's going on.
Yeah, no PhD required, so to speak.
Exactly.
All right, so let's start at the very beginning. Like, what's the basic principle at play here? How does this whole high pressure thing actually work to break cells open?
It's actually a pretty simple concept at its core. Imagine you're trying to, let's say, cut through something really tough, like, I don't know, a thick piece of leather, right?
Oh.
If you just dribble water on it, nothing's going to happen. But if you take that same water and force it through a tiny nozzle at incredibly high pressure, you can cut right through it.
Wow, yeah. Like a water jet cutter.
Exactly.
Yeah.
It's the same idea with high-pressure homogenization.
Yeah.
But instead of leather, we're talking about cells.
Okay. So we're taking a bunch of cells, putting them in a liquid, and then basically blasting them through a tiny space at really high pressure.
Pretty much. And that does a few things. First, you have these incredible shear forces acting on the cells as they're squeezed through that narrow gap. Imagine like pulling something apart from both ends. That's shear.
Right.
And it rips the cells apart.
Okay, so like mechanical tearing, what else is going on?
Well, the sudden drop in pressure as those cells exit that tiny space also causes something called cavitation. Basically, tiny bubbles form and then violently collapse, which further disrupts the cells.
Ah, so it's like a double whammy. You've got the shearing and then these exploding bubbles. Anything else contributing to the cell breakdown?
Yeah, actually. The cells themselves, as they're getting pushed through, also collide with each other and the equipment at high speeds. And that impact, it's called impingement, further contributes to breaking them open.
So it's a combination of a few things. Shear forces, cavitation, and this impingement.
Sounds pretty rough on those cells.
It is, but it's very effective.
So what kind of equipment are we actually using to do this? The material you sent mentioned a couple of key types.
Right, the two main ones are piston gap homogenizers and microfluidizers.
Okay, let's start with piston gap homogenizers. How do those work?
So those are the more, I guess you could say, classic approach. They use a piston, like in an engine, to physically force the cell mixture through a really, really tiny valve at high pressure. It's all mechanical.
And I'm guessing those come in different sizes. Yeah, you can have single piston ones for smaller batches, or if you're working on a large scale, there are multi-piston systems for continuous processing.
So that covers the piston gap type. What about these microfluidizers?
These are a bit different. They work by forcing the cell suspension through these incredibly tiny microscopic channels, actually at extremely high speed. And that creates some seriously intense shear forces within those microchannels.
So instead of a piston and a valve, you're using these tiny channels. Interesting. Now, I'm sure just cranking up the pressure isn't the whole story. What are some of the other things that need to be carefully controlled during this process? You mentioned pressures ranging from 500 to over 1500 bar. Just to give us an idea, what does that sort of pressure translate to in everyday terms?
Oh, it's huge. I mean, we're talking hundreds to over 1,000 times the pressure you're experiencing right now just sitting here.
Wow. So operating pressure is obviously key here.
Absolutely. Generally, higher pressure means better cell disruption, which is what we're after. But on the flip side, it also uses more energy.
And I imagine too much pressure could actually damage the stuff inside the cells that you're trying to get.
Exactly. It's a delicate balance. Sometimes you can actually end up denaturing those fragile proteins or enzymes if you're not careful. So finding that sweet spot is really important.
So it's not just a set it and forget it kind of thing. What about running the cell mixture through the machine multiple times?
That's another factor, the number of passes. More passes definitely means more cells getting broken.
But I'm guessing there's a trade-off there, too?
You got it. It takes more time, of course, and maybe more importantly, it generates a lot more heat.
Oh, right, all that friction. And we just talked about how sensitive some of those molecules are to heat.
That's right. So temperature control is absolutely crucial. You mentioned the material I sent over. It really emphasized how important those cooling systems are. heat exchangers and things like that. You really got to keep that temperature in check to prevent damage.
Makes sense. Now, what about the flow rate? How fast the material is moving through the system? Does that affect anything?
Oh, definitely. Flow rate affects two things, really. The total amount you can process in a given time and how well those cells actually break open. Again, it's something you need to optimize for each specific cell type and what you're ultimately trying to achieve.
Okay, so we're talking about blasting these cells under huge pressure, using specialized equipment, and carefully managing things like pressure, temperature, and flow rate. Now, where is this actually used on a large scale?
This is a pretty common technique in a lot of industries. It's used to break open a wide range of microorganisms like bacteria, yeast, fungi, algae, even mammalian cells sometimes.
So it's pretty versatile, and what's the main goal?
Well, often it's to get at those valuable things inside the cell. Enzymes, proteins, things like inclusion bodies. Those are basically little packets of protein that some cells produce. Really useful
So
stuff.
it's a way to kind of unlock all that potential hidden away inside cells. So let's talk pros and cons. What are the big advantages of using high pressure homogenization?
Well, it's really effective at breaking cells open. You can scale it up pretty easily to handle huge volumes, which is critical for industrial applications.
Yeah.
And it's relatively fast compared to some other methods.
Sounds pretty impressive. But there have to be some downsides, right?
Oh yeah, there are definitely limitations. First off, the equipment itself can be pretty pricey. It also takes a good bit of energy to create those high pressures.
Mm.
And we already talked about how heat generation can be an issue. You got to have good cooling systems. Plus, there's always the risk of damaging those precious molecules you're trying to extract if you push the pressure or temperature too high.
Right, right. Anything else?
Well, and sometimes if you're working with really thick mixtures, you can run into problems with the valves getting clogged.
That makes sense. So, big picture then, high pressure homogenization is a really powerful tool for getting inside cells, especially on an industrial scale. But it's all about finding that balance between breaking things open and not damaging the goods in the process.
Absolutely. It's
Yeah.
powerful, but it requires careful optimization to make sure you're getting the most out of it.
That's a fantastic point. You know, this deep dive has really opened my eyes to the incredible power of high pressure in biology. It's remarkable that we can manipulate cells at such a fundamental level. And that leads me to a question for our listeners to ponder. Given this ability to efficiently access the inner workings of cells, what other applications might this high pressure approach have in the future? Could we even see it used to manipulate subcellular structures in new and innovative ways? Something to think about. Thanks for joining us on the deep dive today,
It's been a pleasure being here.
and we'll see you next time.